So just a little reminder of what we did yesterday. We re-derived Einstein's paper. Am I going to make you re-derive it on a test? Yes or no? No. I did it because it is kind of cool that Pythagoras, little factoring, and ta-da, you get time dilation. And I like to let you know what puzzles his mind was wrestling with. He was really interested in what it would be like to travel at the speed of light. How would things behave? He wanted those answers. In fact, when he was in high school, your age, he says he remembers asking himself, what would he see if he was riding on a beam of light? Would he be able to see anything? Because you see by having light travel to your eyes, but if you're traveling at light speed, would the light just be frozen in place, like little photons sitting? He wanted to know the answers to these questions, and I've had some of you ask me similar questions, not mentioning any names, but you know who you are. Not mentioning any names, but you know who you are. Not mentioning names, you know, okay. These are good questions. So we re-derived Einstein's equation. You don't need to know that, but go from this box, and you can get the notes later, but from this box, everything else is fair game. We said the key thing, really the tricky part here is you need to remember which one is T0 and which one is T. What was the dumb way that I gave you to remember which one is T0? Do you remember? Yeah, I said I don't see a 0. I treat it like a T with a letter O, and I think time on board, O for on board the spaceship, okay? T is the time back on whatever's at rest. Usually it will be Earth. And V is the speed. We usually gave the speed as a percentage of the speed of light. Why? Because then do you see, what do you see? And then we started looking at some examples. Oh, we got someone coming here. So we said, as far as I was concerned, I could ask you to find T back on Earth. I could ask you to find T0 to get the T0 by itself. We said, oh, well, the square root's dividing. We just multiplied it over. We could find how long the spaceship had to travel. And we can also find V. We haven't done that one yet. So, and we noticed that for light itself, how much time does a beam of light actually experience? Nothing. Photons don't experience the concept of time. So let's start with example 6. Example 6 says this. A spaceship is traveling at 2.85 times 10 to the 8th meters per second, leaves the Earth and returns to Earth 100 years later relative to the Earth. How much time has passed for those living on the spaceship? Casey, what is this asking me to find? Which one? T or T0?
T0.
Yes. So let's all write down T0 equals question mark. Sadie, we're on the back page of our formula sheet. Definitely on the back lower half of the page. And Riley, you can kind of show her where the time dilation equation is. So that must mean, Casey, they told me T back on Earth. What's T back on Earth?
100.
Yep. They must have told me V, the speed. This is a bit different. They gave it to me in meters per second. They did not give it to me as a percentage. That's going to be a bit of a pain. We're going to have to do a bit more number crunching because unfortunately, do you see, what do you see, won't work. Yeah. See the time dilation equation on your sheet? Right? Get the T0 by itself. What's the square root doing to the T0? Adding, subtracting, multiplying, or dividing? It's the one that has a T and a T0 in it. I think there's only one. Yeah. What's the square root doing to the T0? Adding, subtracting, multiplying, or dividing? Sit loud and proud. You're right. Yeah, have confidence. You're smarter than you look. Right? Or make that a compliment. So how will I move the square root over? If it's dividing on the right? What's the opposite of dividing on the... Yes, we get this. T0 is going to be T times the square root of 1 minus V over C, all squared. Is that all right? Okay. Let's plug in the numbers. What's T? Yep. And then big square root, 1 minus, what's V? Well, it's 2.85 times 10 to the 8th. Is there a c attached to that because they gave it to us as a percentage? Hey, no. So I'm actually going to have to stick in the number for c, which is also on your green sheet somewhere right near the time dilation equation. What is the speed of light, c, as a number exactly? I think it's near the middle. Yep.
3.0 times 10 to the 8.
I'm not going to bother typing the 0.0. Squared. Sometimes instead of giving us the speed as a percentage of the speed of light, sometimes they'll actually give us the speed in meters per second. Okay, we get out our calculators. Casey, you ready? Here we go. I guess it's going to start out by 100 times. And then square root. I have to open up a bracket. You have a TI. You have to open up a bracket as well inside the square root. 1 minus. Now I'm going to have to open up another bracket because those two things are in a mini bracket. See them? And then 2.85. Ooh, my scientific notation button, which we did, holy smokes, way back at the beginning of the semester, but we did. I remember it's on the TIs, it's the EE button. 8 divided by 3, scientific notation button 8. Close off the mini bracket. Now the squared goes outside that, and then I got to close off the square root. All of your calculators might do it a little bit differently, but really, really grab a calculator and follow along. I do know that time moves slower on the spaceship. What does that mean? I know I better get an answer less than 100. So there's a bit of a built-in error check if you know the gist of how time dilation works. What'd you get? 31.2? Yep. Okay. 31.2 years. Earth experienced 100 years. The astronauts experienced 31.2 years. Example 7. I like example 7. I like example 7. I like example 7. Example 7 is a nice question. Suppose a spaceship leaves the Earth traveling very fast. The phrase we use is relativistic speeds. In other words, you're going fast enough for time dilation to really play a role. It returns 20 years of Earth time later, but only 10 years elapsed on the spaceship. How fast was it traveling? Josh, what's this question asking me to find? Ooh, okay. Did they give me T0 then on board? Yeah, what? Yep. Did they give me T on Earth? I guess I need to get the V by itself. Josh, I used to be meaner. I've mellowed in my old age. I used to actually make the kids get the V by itself. Look at the back of your green sheet. On the bottom, near the bottom, is there an equation that says V equals that also has T's and T0s in it? We're good. I got it by itself for you, but we're going to add a little part A. If you don't mind, could you go part A, give your answer as a percentage of C. What's C in a brief for? Okay, so you can read, give your answer as a percentage of the speed of light, but why would I write out the speed of light when I got a lovely brief? So write that as a little part A. Josh, can you read to me the equation that has the V equals? It starts like this, V equals C, and I know there's a square root, but I don't remember the rest. I'm going to do the T0 over T all squared trick because I think that's a little easier to type. And then, Josh, can you read what I typed here for part A? Give your... I'm going to, on a test, I will ask you to find V. Sometimes I'll ask you to give it as a percentage of C, and here's how we do that. We're going to leave the letter C as a C. I'm not going to put in the 3 times 10 to the 8th. I'm just going to leave it like that. And I'm going to go square root of 1 minus 10 over 20 all squared. And I'm just going to evaluate the square root. So go to your calculator now. This one I happen to have memorized because 10 over 20, this is a 1 to 2 time dilation ratio, and I just, because I'm a nerd, happen to know it's going to be 0.866. Also happens to be just past an A on a report card. Things I've memorized. So try typing that in and see if you get 0.866. And you'll notice this time I didn't type it for you. You're going to have to figure it out. I'm trying to get you to figure this out on your own. So this means if you're not typing this in, you're going to get a stink eye in just a second. So try typing this in. And if you didn't get 0.866, this is your chance to raise your hand and I will come and assist you. Yeah. This is where I have so many different calculators. Emily, this is kind of now where I'm saying, you got to figure out how yours works. Okay? Got it all right? Got it all right? Notice what we actually got. We got 0.866 C. The C I didn't evaluate, Josh. I just left it in the front. I'll tack it on the end. Hey, what percent of the speed of light is that? 86.6%. What did I tell you yesterday that the word of always meant in math? Times. Unless it says to the power of. That's the only place where it's an exponent. Everywhere else, trust me, I got a math degree. I look. Oh, we have a latecomer. Wonderful. There's another way I could ask this. Now, if you have room, and you should, I hope I left you enough room, you can add a little part B. Give your answer in meters per second. How would I convert square root of 1 minus bracket 10 divided by 20, close bracket, squared, close bracket? How would I convert 0.866, 86.6% of C into meters per second? Well, now what I'm going to do is I'm going to take my 0.866, but I'm going to use my answer button. So I'm actually going to use the 0.866025540. And I'm going to actually just multiply it by the value of C. Oh, Casey, what was C as a number again?
3 times.
Yeah. In other words, how do you find 60% of a number? You go 0.6 times the number. How do you find 86.6% of C? You go 0.866 times 3 times 10 to the 8th. I will ask you both of these somewhere on a test. Or I may ask you for both answers in one question. So I'm going to go answer button times 3 times 10 to the 8th. In meters per second, we are going at 2, 5, not, you know what? I'm going to write this in scientific notation. There's a 0 after the 8. That seems like a nice place to stop writing. So I'm going to go 2.598 times 10 to the what? So try this on your calculator. Don't just copy from me. You've gone answer button times 3 times 10 to the 8th. 2.598 times 10 to the what? Let's see. 1, 2, 3, 4, 5, 6, 7. I moved the decimal point. Of course it's times 10 to the 8th because it's almost the speed of light, and the speed of light is 10 to the 8th. So I'm okay with that. And units, meters per second. A couple more. And then we're going to be going over the kinematics test. Those of you that haven't written, I'll ask you to go wait outside for a bit, but then you'll have plenty of time to practice this too. Example 8. By how much is time expanded, or the clock slowed, if a spaceship is moving at 1/2 the speed of light? What's this question asking me to find? This question is kind of vaguely worded. It says, by how much does time expand? Oh, from a fixed observer's point of view. Fixed observer's point of view, is that t or t0? Okay, this, I guess, wants me to find t. Diego, question? You sure? You good? Well, what's v in this question? Okay. What's T0 in this question? They didn't give it to me. So here's what we're going to do. We're going to assume T0 is 1. One year on the spaceship, or 1 minute on the spaceship, or 1 second on the spaceship, or 1 day on the spaceship is equal to what on the Earth? Let's find out. The t is by itself. We're going to use our time dilation equation. T equals T0 all over the square root of 1 minus V over C all squared. And I'll just put in a 1. And 0.5 C over C all squared. Diego, do you see? Do you see? Do you see? What do you see? Yeah. So it's going to be on my calculator, fraction button if you have the fancy schmancy fraction button. Otherwise, I don't need brackets around the top. Definitely need brackets around the bottom. Square root bracket, 1 minus 0.5 squared. Close off, close. You get 1.1547? I'll go 1.15. Units, well, they didn't give me a time unit. This is actually the time stretch ratio. 1 second on the spaceship is how many seconds on the Earth? 1.15. 1 hour on the spaceship, how many hours on the Earth? 1.15. 1 day on the spaceship, how many days on the Earth? 1 year on the spaceship, Alex, how many years back home on Earth? Thank you, Sadie, for figuring out and spotting the pattern. Alex, 1 decade on the spaceship, how many decades on the Earth? 1 hour on the spaceship, how many hours on the Earth? So at half the speed of light, it's noticeable. But even that's not like crazy skewing things. You're off by about, 15%. Okay. But it's not like you'd be coming back and finding everything changed. Let's go a little faster. What if we go at 80% of the speed of light? So the same question, but now let's do it for 80%. You know what? Since it's exactly the same question, we're just changing the percentage. I'm going to make my list still. I'm going to say, okay, they want me to find t. I'm going to assume t0 is 1. V is 0.8 C. But have you all got good calculators? If you can, on your calculator, just backspace and edit, you can change the 5 to an 8. And you're good. Now, if you haven't figured out how to backspace and edit on your calculator, because I think every one of your calculators can, you might want to start to dig into the manual, because that's going to come in handy this unit. I mean, you can type in the whole thing from scratch too, but why? And I get 1.67? Yeah? So Bryce, if 1 second goes by on the spaceship, how many seconds go by back home on Earth? If 1 minute goes by on the spaceship, Casey, how many minutes go by on the Earth? Okay? This is the time stretch ratio, the time dilation ratio. Now, little note. Up for now, we have been assuming that A equals 0. Einstein at this point, this was around 1904 and 1905. He did not know how to work acceleration into his equations. In fact, the theory of special relativity, it should really be called the theory of special case. relativity. And Lily, what's the special case? Oh, A is 0. The theory of general relativity, that allowed him to include accelerating objects. But that took him 10 years of heavy-duty math. He had to invent a branch of math called tensor mathematics, tensor field mechanics, and it's intense. It is not Math 8, Pythagoras, and a little bit of factoring. It's really intense. But it also allowed him to include acceleration, and because gravity causes things to accelerate, it led to a much better explanation for gravity. At the end of this unit, I will do a little day-long lesson on general relativity. It won't be on your test because the math is crazy, but I'll explain the concepts behind it because it is pretty nerd-tastic. Meanwhile, what's your homework? Your homework here is every question. I've put the answers at the very, 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 very end, and on Teams, I'll send out an answer key showing all my steps as well in case you're getting stuck on something. All right?